Ah, perfect.
Yeah. Let's just start.
Yeah, I think Arshil started with that's good. So should we wait 2 more minutes or and then we get started?
Okay, I'll stop
Yeah.
recording right now and then I'll continue. Okay.
Ah, yeah, good. Thanks, Arshil, for recording. There's I'm
no
actually
problem.
not sure whether I can or not.
Yeah, no problem.
As part of permissions. Everyone, to the Sydney CPPC seminar. So this week's speaker, our speaker is Dibyendu Nanda from KIAS. Dibyendu obtained his PhD in 2021 from the India Institute of Technology at Guwahati, and then moved on for postdoc in Kolkata. And since last year, he is at KIAS. And he will be telling us about imprint of non-thermal leptogenesis in CMB. Yeah, please.
Yeah.
Over to you.
So, yeah, thank you for the introduction. And first of all, I'm to also thank for the invitation to present my work here. So I'll try to talk about one of our recent work where we have discussed the possibility of looking for the imprints of non-thermal leptogenesis from the observables of cosmic macro background. So this work is based on this archive number. You can check, although the present version is quite different than this one. So first I want to discuss the introduction, which is already known to most of the listeners, but for the completeness of this presentation, I'll include that. Then I'll discuss the motivation about this work. After that, I will discuss two different scenarios, two different cases we have studied, where we have shown how can you connect the parameters responsible for non-thermal leptogenesis or responsible for generating matter-antimatter asymmetry and with the inflationary observables. Then I'll discuss the results and I'll conclude. So as we already know that most of the structures of the universe, they consist of ordinary matter, and the so-called matter-antimatter asymmetry, which can be parameterized by this eta, which is the ratio between baryon to photon numbers. So that has been measured quite precisely and quoted, can be quoted like this, which is of the order of 10⁻⁻10. And this quantity eta, so both the cosmological observations, like observation of Big Bang nucleosynthesis, which occurred approximately 1 MeV of the temperature of the universe, and the observation of cosmic macro background, which is of the order of 1 electron volt. So both these observations, which are almost 10⁶ order of magnitude different in terms of temperature, both of them both of them agrees with this number. So then the question is, indeed there is asymmetry between matter and antimatter. Then what are the theoretical origin, or how can we generate such asymmetry dynamically? There are many different possibilities have been already been discussed in the literature. Leptogenesis is one of them. So, by the way, if you can stop me at any time and you can ask me questions. So here we are assuming that leptogenesis is the correct theory of nature, and that's how the matter-antimatter asymmetry have been generated in the universe. Now, if so, then we already know that the basic ingredients of leptogenesis, or the type 1 leptogenesis, is the standard model particle content, and you have to add 3 or at least 2 right-handed neutrinos to generate the correct neutrino mass. So what I mean is, if you have standard model and if you extend the particle content by right-handed neutrinos with heavy right-handed neutrinos, you can generate the light neutrino mass through type 1 seesaw mechanism. At the same time, you can also generate leptogenesis from the decay of these heavy right-hand neutrinos. So just by extending the particle content of standard model by 3 or at least 2 right-hand neutrinos, you can solve two puzzles of the nature. So what will happen if you just introduce heavy right-hand neutrinos in your theory? So you can write down these two new interactions in the Lagrangian. One is the Dirac-Yukawa coupling, and the other one is the Majorana mass term for right-hand neutrinos. Now, if you use this and apply it for generating the light neutrino mass through type 1 system mechanism, you will get this formula, which is a relation between this Yukawa coupling and the Majorana mass. So from the neutrino mass, there is already a constraint, or there is already a relation between this y nu and mn. And again, these ends which can generate matter-antimatter asymmetry through this interference between this tree level and these loop level diagrams. Here also, these two parameters will play the main role. Now, so it's an elegant theory which can solve two different puzzles of the universe at the same time. But what are the observational consequences of that? If you introduce these right-hand neutrinos, is there any observational consequences or not? So let's first understand that if we want to generate the order, 0.1 order of electron volt neutrino mass, by assuming that y nu have to be order 1, this mn have to be very large, like 10 to the power 13 to 14 G. Now, for successful leptogenesis or for successful thermal leptogenesis, I'll explain difference between thermal and non-thermal in a few moments. But for a successful thermal leptogenesis and correct neutrino mass, this mn have to be greater than 10 to the power 90, which is the so-called Davidson-Nevada bound. So this the main point is this order of mass is inaccessible, is not accessible or inaccessible to the conventional laboratory experiments. Obviously, you can make this scale lower by introducing some new particle to your theory by sacrificing the minimality of this standard model plus 3 right-hand neutrino scenario. But here we are assuming we have only standard model plus 3 right-hand neutrinos. Now, as I said, depending on this Yukawa coupling and the masses, you can divide this leptogenesis in two different scenarios. It can be either thermal or non-thermal leptogenesis. By thermal, I mean these right-hand neutrinos can be present in the thermal bath of the early universe. Whereas in the non-thermal case, it will be the opposite. Like it will never be in the thermal equilibrium. The one possible way to ensure that non-thermalness of the right-hand neutrinos or the thermalness of the right-hand neutrinos is the mass of the right-hand neutrinos can be, if the mass of the right-hand neutrino is heavier than or larger than the maximum available temperature in the thermal bath, it will never be in the thermal equilibrium. So if the right-hand neutrinos are heavier than the maximum available temperature, the thermal bath of the universe will never have the sufficient energy to produce it in the thermal plasma. So what do I mean with Tmax? So the thing is, if you plot the temperature of the universe as a function of scale factor, for the timing, let's forget about all these parameters. You can see here that it's a temperature as a function of scale factor. Now, this temperature is known as Tmax, whereas the reheating completes around this temperature. So you can see the reheating temperature is a few order of magnitude smaller than the maximum available temperature of the universe at very early time. So to ensure that right-hand neutrino was never in thermal equilibrium, one possibility is that if these right-hand neutrinos are heavier than this maximum available temperature, that is the Tmax, it will never be possible to produce those particles in the thermal bath. So now that's the first case. That's how you can ensure the non-thermalness of the right-hand neutrinos. But the next question is, here we are interested in non-thermal leptogenesis instead of thermal leptogenesis. Then the question is why we are interested in non-thermal leptogenesis. The reason is that in the case of non-thermal production of any relics, if you produce something which was not present in the thermal bath, it can remember its production history, which is quite different than the case of thermal production. because if you produce something in the thermal bath, once it enters in the thermal equilibrium, it will always follow its thermal number density, and eventually it will freeze out, or you will decouple from the thermal bath when its interaction rate will fall below the expansion rate of the universe. But in case of non-thermal production, I mean, because in this case, you don't have to follow it. It doesn't have to follow the thermal distribution. It can remember from where it from where it was produced, and because by using that fact, you can indirectly constrain its mother particles, or its source actually. So that's the reason we are trying to or we have focused in the non-thermal representation. Now the next question is, how can you produce such heavy right-hand neutrinos in the thermal bath if they were not present in the sorry, how can you produce those heavy right-hand neutrinos in the early universe if they were not present in the thermal bath? So they can be produced from the decay of directly from the decay of the inflaton. So the picture will be so you have inflaton, which is a scalar field which is responsible for inflation. Then inflaton can decay directly to the heavy right-hand neutrinos, as well as it can also produce a thermal plasma, which is known as the reheating process. Now, these heavy right-hand neutrinos, as I showed, it has this Dirac-Yukawa coupling. Through that Dirac-Yukawa, it can generate the matter-antimatter asymmetry through leptogenesis. At the same time, it can also decay, or it can also contribute in the reheating process. So the thing is, there are two observables which will be very crucial in this discussion. The first one is reheating temperature. Reheating temperature is defined as the temperature when universe starts to dominate by radiation, and this is the asymmetry parameter. So the more the game is like, the more energy you are extracting from the inflaton to the right-hand neutrinos, the less the smaller the reheating temperature will be. So if you want to produce more asymmetry, you need more right-hand neutrinos. If you to increase the right-hand amount of right-hand neutrinos, you need to increase this coupling. Once you increase this interaction, this contribution will decrease, and you can see that TRH will change. So that's the game basically. Now let's discuss how can it really help us to look for the imprints of it. As I said, so initially in the standard mechanism, after inflation, inflaton decays to the radiation particles to form the thermal bath, which is the so-called reheating process. Now, if this reheating is not instantaneous, you can define a parameter, which is the number of E-folds from the end of inflation to the end of reheating process. So, I mean, this can be parameterized by this rho RE and rho end, where rho RE is the reheating temperature at the beginning of the radiation dominated era, and rho end is the energy density at the end of the inflation. Now you can see that rho RE depends on this coupling, inflaton to the thermal bath, and rho end depend on the model of your inflation, what kind of inflationary model you are considering. So here for our illustration, we have considered alpha attractor model. So which can be, this alpha attractor model can be parameterized by two parameters. One is alpha and one is n. One is alpha and one is n. All these other parameters like lambda, can be expressed in terms of n and alpha. Now, and of course the mass of the inflaton. So all of them can be parameterized by alpha and n. Now the observables we are interested in is the spectral index NS, which is parameterized by these flow rule parameters epsilon and eta, and the tensor-to-scalar ratio R. So the Planck observation of CMB data, they constrain the parameter space of this NS versus R plane very precisely, or they are very tightly. So so what we did, or what I will show you, is that the imprint of these non-thermal representances in principle can be constrained in this NS versus R plane. So if you have this alpha attractor potential, which is this, and then you can calculate or you can derive a relation between this tensor to scalar ratio R and spectral index like this. So that's the good thing about alpha attractor model, that there can be a relation between, or there can be a straightforward relation between R and NS through this alpha and N observables. Now the next job is, can we relate this NSR with the parameters of leptogenesis? So to do that, let's first define that at horizon exit, we already know that for any mode K, it can be, so these relation holds like ln of K by AK is K equals to 0. Now, if you play with these observables, like if you can just reparameterize this equation by this quantity, then you can finally convert this relation to this relation, like NRE, which I have showed that it depends on the ratio between rho RE and rho N. You can also express NRE in terms of these other parameters like NK, V end, and R. Now, these are all of, I mean, out of all these parameters, what the important thing is that this, you know, all these other things except NK, but NK can be expressed in terms of maybe if you know the inflationary potential, that is the alpha attractor, you can express this NK in terms of N alpha and NS. So in principle, NK can be expressed in terms of NS alpha. At the same time, Vn also can be done. I mean, Vn can also be expressed in a similar fashion. So what I mean is, NK and V end, both of them can be expressed in terms of alpha end and NS, where alpha and N are the are the parameters of the alpha attractor potential, and NS is the observable we are interested in. At the same time, you can see this also depends on R. So now the point is, as NRE can be expressed in terms of this ratio, rho RE by rho end, which this rho RE depends on the parameters which connects inflation and the thermal bath. And so this, if the next job will be to equate this part with this part. So you can see these are coming from the your model, like model of inflation and model of leptogenesis. And this part is also depends on the same parameter and the observables like NS and R. So what I'm trying to say is, if you have this, if you want to produce these heavy right-hand neutrinos from the decay of inflaton, that basically means you are extracting some energy from the inflaton sector to the right-hand neutron sector. That what is that doing? That is effectively decreasing this rho RE. And if you decrease rho RE, that will directly affect NRE. And if you change this NRE for a fixed value of alpha and N, I'll show you that it will directly affect this NS and value of NS and R. That's the thing. So to do that, we first restrict ourselves to N equals to 1. This N, which is the parameter for the alpha attractor potential, we fixed it for N equals to 1, because for N greater than 1, this potential exhibits a 0 mass at its minimum, but we don't know that, because in our case, inflaton have to decay to right-hand neutrinos to heavy right-hand neutrinos, so it should have some should have some non-zero mass at the minimum. And the secondly, this other parameter omega RE, this can be expressed in terms of N minus 1 by N plus 1. If you put N equals to 1, it will be 0. So effectively, the important parameter from the alpha attractor potential will be alpha. So now let us consider the this following Lagrangian. What we are saying, that N is producing from the decay of inflaton. This phi is inflaton in other right-hand neutrinos. X is a bath particle, so phi is decaying into the bath particle through this coupling YR, and this is the Dirac-Yokov coupling. So this is the picture. So let's discuss the results. What will happen if we is it possible to constrain this right-handed neutrinos, and is it possible to constrain the these couplings like Y and R, or the mass of the right-hand neutrinos to this NS versus R plane? So as I said, so this phi can decay to two particles like radiation and the right hand neutrinos. So we have to solve know the evolution of these energy densities. We have to solve these coupled Boltzmann equations. I would like one equation for phi, for radiation, for right hand neutrinos, and for asymmetry. You can see that this phi is coupled with basically the energy density of phi is going into two sectors, as I discussed quite a few times. Like it's contributing to the radiation, as well it's contributing to the right hand neutrinos. So the basic thing is, if you or the important thing is, if you increase this decay width, the whole contribution to this sector will decrease, and that's how it will be connected in the NS versus R thing, NS versus R plane. So here we are showing the evolution of these energy densities, as I discussed in the very beginning, that there are two different temperatures involved. One is the T max and one is the T reheating. So you can see that, as I said, that reheating temperature is defined when the universe starts to dominated by radiation. So this is the reheating temperature. But if you track the temperature as a function of scale factor, you can see the actual maximum available temperature is this one. So that's the T max. So you have to ensure that the right hand neutrinos are always larger or heavier than this maximum available temperature. And the other important thing is, here in this work we have assumed that the energy density of the universe was never dominated by n. So you can see n is always the energy density of n is always smaller than the energy density of the radiation. So the energy density of the universe was dominated by inflaton first, and then by radiation. Now, in this plot, we have fixed the observables like fixed the parameters like alpha equals to n, alpha equals to 5, yn equals to this, and the yr equals to 10 to the minus 6. Now, let's here we have shown the asymmetry ybl as a function of yr, and you can for the fixed values of yn, theta, and mn. Another important part is the theta is the the CP asymmetry is can be parameterized by theta, which is a mixing angle is coming from the Casasibara parameterization. Now you can see that this asymmetry as a function of yr decreases with increasing yr. This is it can be understood as follows, that if you fix yn, that is the coupling between inflaton and the right hand neutrinos, and if you continue to increase yr, what you are actually doing, you are taking away more and more energy from the inflaton to the radiation sector or to the thermal bath. That's why the contribution to the right hand neutrino is decreasing, and as the total number of right hand neutrinos will finally decide the amount of asymmetry, that's why increasing yr will decrease the asymmetry. And you can see that for a fixed value of yn, theta, and mn, that's the only values. This orange line is the amount of correct asymmetry you need. So this is the only value of yr which is allowed from the requirement of generating correct matter-antimatter asymmetry. Now, if you collect all these points for different values of yr and yn, or what I mean for different values of alpha. So here we have shown for different values of alpha, like alpha equals to 1, 5, and 20. And okay, so another important thing is, if you there are also dependence on alpha, as you can see for different values of alpha. You can see these lines are going if you increase alpha, this line is going down. This is again because if you can see this m phi is related with alpha. So if you increase alpha, that basically means you're decreasing m phi. And if you're decreasing m phi, that will affect this decay width between phi going to n. Decreasing the mass of the mother particle means you're decreasing the decay width, and that's doing the same thing as by fixing everything, increasing yr was doing, it will do the same thing. So now if you try to collect these points and vary yn, what you will see is a correlation between yn and yr. So all these lines are so we have shown these lines are for a fixed value of alpha, which satisfies the correct amount of asymmetry. matter antimatter asymmetry. Now, again, for different values of alpha, you can see there is a small variation between from alpha equals to 1 to alpha equals to 20. Now, the other important thing we have shown here is that now let's vary this as a function of mass of these heavy right hand neutrinos and this YR, again for different values of Yn. So there is a typo, it should be like Mn less than Tmax. So here we are showing three different constraining regions. The first one is that M phi have to be greater than the twice of Mn, otherwise phi will not decay to the right hand neutrinos. So this part is constrained from that condition. This part is constrained because, as I said, the right hand neutrinos have always right hand neutrinos have to be heavier or larger than the maximum available temperature to the thermal bath. So this part can be constrained. Now, the other thing, again, it's from our assumption, is that the branching ratio of phi going to Nn is always okay. So universe. So the universe was always radiation dominated. So if branching ratio of phi going to Nn was greater than the phi going to XX, the universe will be dominated by N. So if you take this assumption, so this is the only allowed parameter space. And from this, out of this, if you put the constraint of correct amount of matter into asymmetry, you can see only one lines are allowed if you fix the value of Yn. But what will happen if is there a correlation between Ns and R, or between all these parameters if you vary everything like Yn, Yr, all these parameters? So here we have shown that if you vary R and Yn together, like the coupling between the inflaton, the radiation and inflaton with the right hand neutrino, you can predict the value of Ns, as I showed, which in terms of this NRE, you can see that even you're heading alpha from 1 to 20, you can only get the variation of Ns from around 0.965 to 0.9615 to 0.965, around this thing. So this is a very small variation in Ns, even if you vary all the parameters. And the same thing can be shown in terms of R versus Ns, as I was saying. So this parameter space is already constrained from the Planck data. So this, you can see that let's understand this this result carefully. So as you see, if you don't put the constraint, or if you don't assume this condition that your non-thermal leptogenesis is happening because of the presence of heavy right hand neutrinos which are coming from the decay of inflaton, so these points will not be there. So in that case, all these lines are showing different values of alpha, and these are the prediction which is coming from the reheating temperature. So if you have coupling between inflaton and the thermal bath, you can, if for a fixed value of coupling constant, you will get a fixed value of reheating temperature, and that will give you a fixed value or fixed combination of Ns versus R. So now, on top of that, if you impose the condition that the right hand neutrinos are also also produced from the decay of inflaton, and then it is producing the correct amount of asymmetry, then out of all these parameters, out of all these lines, only this part will be allowed from the condition of correct amount of matter antimatter asymmetry. And you can see that this, this sum of this part is already excluded from the 2 sigma band of Ns versus R. And if you consider the 1 sigma band seriously, then also, then the most of the part is already excluded. But the other important thing is, so we have varied all these parameters like YR, Yn, all these available parameters, but still you can constrain a significant amount of parameter space of the model. And so this orange part is showing the NRE, where NRE will be negative, so which is not physical. And this green band is showing the reheating temperature, which is very close to BBN. So this is already excluded from the observation of Big Bang nucleosynthesis. So that's the main point is you can constrain your model of non-thermal leptogenesis from the Ns versus R plane by imposing these conditions.
Can
Second.
I ask one quick question? Sorry.
Yes, sure.
I think I missed one point. So why are you constrained to those points there specifically to that region? So why can't you have larger NS or smaller NS? So if I go
this part.
Yeah. So exactly, but why are you exactly constrained to that part?
Okay, so the thing is, you can see that. Okay, so firstly, this color coding is for alpha. Like if
That's for alpha. You consider values of alpha between 1 and 20. Okay, that's
from 1 to 20. Yes.
And what constrains it again to go to larger or smaller values of NS? That was.
So that's coming from this thing. You can see that if you increase YR, this NS is actually, if you see the left-handed plot, a left side plot. So if increasing YR, even if you fix everything, this NS has a very small variation, right?
So okay. I see.
Yeah.
So I understand.
Change in NS is
that
very,
makes sense. So it's
yeah.
the dependence on YR, and you basically vary YR technically between 10 to minus 4 and 10 to minus 7.
Yes.
Okay, good. Thanks.
Yeah. And so the thing is, then we have, as I thought, so there's a relation between NSR, or you can constrain the parameter space of your non-formal representations through NS and R plane. But to check that, so the first thing here we have assumed in so far discussion, we have assumed that inflaton is decaying in two sectors directly, like inflaton is decaying to produce the correct amount of asymmetry. Sorry, inflaton is decaying to produce the thermal bath, as well as it's producing the right-handed neutrinos. But what will happen, or if we study the another possibility, like inflaton only goes to the heavy right-hand neutron sector, and then these heavy right-hand neutrons are doing two things together, like it's producing the thermal bath, as well as it's generating the correct amount of asymmetry through the same coupling, like the Dibyendu coupling. So will we still get the same correlation or not? So to do that, we have just forbid these two, forbid these couplings, and we have assumed that these are the two UCAWAs which are doing everything now. So in that case, this part will not be there anymore because there is no phi going to radiation coupling. So this is the picture. Now, if you do that again, so that you can see the same thing is same thing. I mean, sorry. Now, what you can see is that this asymmetry YBL actually increases as a function of YN, which is again expected because as there is only one coupling now, so YN, which is the coupling between inflaton and the right-handed neutrinos. So increasing YN basically means you are producing, right-hand neutrino faster. So if you're producing right-hand neutrino faster, so in that case, those right-hand neutrinos are finally getting converted into the matter-antimatter asymmetry. But in this case, the good thing is that we have only one parameter, like Yn, which is extracting the energy from the inflaton to the right-hand neutron sector. But when we calculated the contribution to NS and R, or the correlation between NS and R, we get the same thing. You can see that the similar pattern you can see, although there is a very small variation in the value of NSR, like it is, in the case of, in the first case we have discussed, in the second case we have discussed, like this whole region is slightly moved to the left hand side. But the other correlation is that in this case, if you have only one coupling, which is responsible for this decay of inflaton, you can see that there is a direct correlation even between Yn. As I was discussing before, that increasing Yn is producing more right-hand neutrinos, or faster, you're producing decaying faster, and because of this faster decay, you can produce more amount of asymmetry. And more amount of asymmetry is because if you produce more amount of asymmetry, you can produce larger value of NS. So this is, you can understand is that. So you can see that this orange region is excluded because its NRE is negative, or NRE is less than 0. That basically means if NRE is very small, NRE is effectively the time which in a time or the epoch which is at the end of the from the end of the inflation to the starting of the radiation nominated era. So if NR is small, that basically means reheating temperature is large. And if NR is large, that basically means your reheating temperature is small. So that's the relation. Now you can see that if you go to the larger YN region, that is this side, it's going to the smaller NR region, and that basically means your heating temperature is large, and that's why NS actually increases. And okay, so what I mean to say is that in these two cases, even if your right hand neutron is not generating the in case the inflaton is decaying to the right hand neutron as well as thermal bath, or inflaton is decaying to the only right hand neutron, and right hand neutron is doing the both, like generating thermal bath as well as generating matter-antimatter asymmetry, you can get the same correlation in these two cases. And this was not the case if you don't consider this non-thermal leptogenesis constraint. So to conclude, we have discussed the impact of non-thermal leptogenesis in the inflationary observables like NS and R. So for the illustration purpose, we have assumed, or we have considered the alpha attractor inflationary model. But you can do the same. You can play the same game with other inflationary models as well. But the one good point, we had taken alpha attractor model because there is a straightforward relation between R and NS. Now, if you take other model of inflation, this relation will change, like the relation between NS and R, and prediction, the pattern can be different in that case, but this correlation between NS and R will still be there. So we have considered the presence of heavy right hand neutrino, which are generating the correct amount of matter-antimatter asymmetry through leptogenesis, and these right hand neutrinos are produced from the decay of the inflaton itself. So finally, it can lead to a very stringent constraint in the NS versus R plane, and the future experiments like CMB stage 4 or LitBird, they can constrain this scenario even more, or it might get excluded in a future observation. Thank you.
Thanks a lot, Dibyendu, for a nice talk. We have time for questions. Who would like to go first? Maybe let me start. So in those Boltzmann equations which you showed, it looks like that you only included decays and inverse decays and no 2-to-2 scattering processes. Is that right?
Yes, we have considered only decays, no 2-to-2 scattering.
So how much do you think will kind of wash out due to those 2-to-2 scattering processes affect the leptogenesis?
No, I think it's not. It will not. I mean, the point is, it will not wash out because it's a non-thermal leptogenesis. So the scale of the right hand neutrino is well above the temperature of the thermal bath. So there is, you cannot produce right hand neutrinos even through inverse decay.
Yes,
we didn't even
right.
consider the inverse decay. That's why.
Yes.
Because it's almost negligible.
So temperature is very okay. Yeah, temperature is small compared to the external.
Yes,
that's right. All right.
And that's why we didn't consider this inverse decay process.
That's right. And the other thing what I noticed is if I compare your slide 34 where you showed that band when you switched off YR, and if I compare the one that band when you showed exactly that one, it's basically exactly the same. So so technically that's just set by the inflationary model, right? So there is no
which one? This relation?
No. So sorry. I mean the bands where you have your points, right? That's basically the same as if you go to equation. So to slide 34. When you
exactly. So it's almost. I mean, there is very little deviation from this line, like 0.96. I mean, it's a third decimal place difference, but effectively it's the same It's a same patch we are getting from these two cases, like 1 and 2.
So
And
how
the
well
reason
can you
is,
then distinguish the two scenarios? It's probably
no,
you
I mean,
cannot, or
no, you can, we cannot. The reason is that, I mean, the reheating is happening. I mean, it finally depends on the reheating temperature and the amount of right-hand neutrino you are producing. Now, even if, I mean, even if this is the first thing, and the second thing is that this dependence on R and NS, it's actually coming through the calculation of TRH, not the asymmetry. We are fixing this whole patch because if you fix the, I mean, the amount of right-hand neutrino, the other part is already getting fixed. Like, if you, what I'm trying to say is that, yeah, so you can see that these things, like if you change YR and keep everything fixed, YR is effectively changing the reheating temperature.
okay. So basically, from the additional input of the B minus L asymmetry, you fix one
that
of
patch.
the
Yes.
One of the parameters which is relevant for
the reheating,
inflaton decay, for the reheating.
Yes. So that's the thing. So that's why this whole patch actually depends on the reheating temperature. Now, if you say that, okay, I need that amount of right-hand neutrino, then this whole patch will be, I mean, will be like squeezed, or will be, yeah.
Okay, I see. So it's basically, so still the result is more or less, when you do the CMB observation, you maybe determine in S and R,
Yes.
and you're hopefully in that band. But it wouldn't tell you directly which scenario it is, but you could now pinpoint
actually,
down what is your coupling by R, assuming you have the alpha attractor.
Yeah, and it's you can also think in the other way around, like if non-thermal leptogenesis is true, then NS and R have to fall between these pairs. I mean, of course, it depends on the other model of inflation. We are
so it depends on the model of inflation, right? That's
yes. If that relation might change in I mean that line will change in case of other inflationary models. So we're trying to see. I mean, we're trying to study that now, but effectively, what we are seeing is that still there is a relation. Even if you change the model of inflation, there is still the relation between R and NS will hold. The pattern is getting changed a little bit. I don't have the plots here right now, but in case of other inflationary models, the pattern will change, but still you can see a correlation between NS and R in case of other model of inflation. Because effectively it's the amount of energy density stored in the inflaton. That's just how exactly or how fast you are transferring that to the right hand sector and thermal plasma sector. That's the point actually.
Yeah. So that's basically the main thing which affects it. Okay, that's good. Yeah, thanks. Do we have other questions? Everyone is quiet. So there was another thing what I'm wondering about. So when people study reheating, and there was some people argue that one should take into account so that Boltzmann equations don't properly describe it, that you have to go to those Kadanoff-Bain equations, that you have to go to those non-equilibrium UFT. Do you have an idea how much that may affect the result? That's basically when you go technically far away from equilibrium here in that.
Sorry, I don't have an. I mean.
Yeah, no, that's fine. That's fine. I'm just curious. That's what.
But can you just repeat the question again, please? I mean, I didn't really.
No. So sorry. So what I'm wondering is about. So right, Boltzmann equations are classical, and there are some people who argue that you should go to use Kadanoff-Bain equations, kind of the quantum version. And so I'm wondering how much that will affect the results. Do you expect there are larger corrections or not? So
sorry.
That's fine. That's fine.
Yeah.
Just because you cited you mentioned the paper by Marco Treves, and he is working on those things. That's why I was wondering whether
Okay.
you looked. Okay, that's good. Okay, it's interesting that you can use that to constrain it. So okay, but in the end, in order to pin it down, really, you would you really have to pin down the inflationary model as well.
Yes, I mean, that's a crucial point, I guess. If you change the model of inflation, how much this prediction will change, that I mean, that is the main point.
Yeah.
I mean, if that falls very close to NSR and R, I mean, even if the pattern changes, but it falls close to this, maybe then we can claim that it can be probed. But yeah, if it drastically changes, then yeah.
Okay, that's good. Yeah. So thanks a lot.
Yeah.
Any
Thank
last
you for
question
the invitation
for anyone? Well, if not, then yeah. Thanks a lot once more, Dibyendu.
Yeah. Thank you.
Thanks.